Okay, this is the 2000 AP Physics C for your response question, the first one, and this is our video for Dylan and Alex. And so the question is asking, um, it gives you some of these periods, and that's the time for 10 full oscillations with a mass, I think, at the a simple pendulum, so a mass at the end of a string, a weightless string. Um, and so there are different lengths, and each length has a different time for 10 periods. So instead of using these values um, for our project, our video, we calculated these on our own. So we built one of these apparatus, one of these apparati, and we got different values for period for 10 periods. So um, here's the first one. 7, 8, 9, 10. So that gave us a time. Um, that was the 12 centimeters. That gave us a time for 10 centimeters of 6.122 seconds. And so I'll do the next one, 18 centimeters. Here it goes. 2, 3, 4, 5, 6, 7, 8, 9, 10. So 18 centimeters, that was 10 periods of 7.957. 957. Let me just rewrite these in thinner things. So this first one is 6.122. Second, 18 centimeters, was 7.957 seconds. And here's a 21 centimeter one. 1, 2, 3, 4, 6, 7, 8, 9, 10. So 21 centimeters length gave, where's my pen? Gave 8.748 seconds for 10 periods and 10 full oscillations. Here's a 32 centimeter one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that last one of 32 centimeters took 11.169 seconds for 10 oscillations. So when we're finding the period of each of these, pretty obvious. This is for 10. This column is for 10 oscillations. So we divide each of these by 10 to find the period, and that doesn't take a calculator to do. Just move the decimal place. So this would be 0.612 seconds for one period, and this would be 0.796 seconds, and this would be 0.875 seconds, and this would be 1.117 seconds. So I do need a calculator to square them. Hold on. Okay, so I did question B. I plotted the points um, according to these two values, L and T squared, and and then I did a best fit line, best fit straight line, using this little tool in this program, which is handy, but in the test you'll have to draw it yourself. And you don't get a ruler, so use something else. So anyway, so B is done. And C, so it wants you to find G experimental using this line from your fit, and it's at an unknown location, so it they don't want you just to say 9.8 because it's probably not going to be. But since our group did it on Earth in a physics lab, I guess I shouldn't tell you that, but that's where we did it. So it should be 9.8. We'll see what happens. And so the way you do this using L and T squared, that relationship, page. So the proof is so this little pendulum, that's it. And so the line is massless, and the mass is all the mass. So let's see the force diagram. So we have mg coming down here, and here perpendicular to that. This is theta. So here we have mg sine theta. And so we can write this torque thing. This should be easy. This should we do this a lot. Mg sine theta. And here this value is L. And that's so torque is force times distance from the pivot point, which is L. So that's the force, mg sine theta times L. And you can also write that as I alpha. And alpha can be defined as theta double prime, which equals d squared theta dt squared. So the second derivative of theta according to time, and I assume that theta prime is d theta over dt. But we're using this because it's alpha acceleration, angular acceleration. So and here inertia, this definition, since all the mass is at the end, and it's L distance away from the pivot point, the definition of inertia of a simple pendulum is just the mass times the distance squared, where the distance is L. So we can rewrite this as mg sine theta equals ml squared theta double prime. And so the m's cancel out. Sorry, there's supposed to be an L. One of this, so both one L on each side, and then using, remember the small angle approximation, I'll just quickly draw it. Sine looks like this, and y equals x. Oops. Y equals x looks like that ish. And so in this little area, you could say theta equals sine theta equals theta, where theta is x. So in this little area, and that's usually meant to be given at between 15 degrees on either side. So that's why we don't pull it so far back. We just have to pull the little pendulum, try to make it less than 15 degrees in order to keep this true. So we can rewrite this as g theta equals L theta double prime. And so g G over L theta equals double prime theta. And this is a relationship we should be familiar with, where the coefficient of theta equals theta prime. That coefficient is omega squared. So omega squared equals G over L. That should be something you know. And so omega equals root G over L. And so the definition of a period can be 2 pi over omega. So that would be, in this case, 2 pi over root G over L, or 2 pi root L over G. And so now we have a relationship between T and L, but so our graph here is T squared and L, so let's square both sides. That will help. Well, it's actually, this one's in terms of T and L squared, or L, square of L. So T squared equals 4 pi squared times L over G. And so T squared equals 4 pi squared over G times L. So here is the very useful equation where this coefficient in front, use another marker, this little coefficient here is the slope of that graph over there. So over here, that's the slope of that line. And so we can say that the slope of that line, m, equals 4 pi squared over g. And so when we find the slope here, we can do that now. So here's a point, easy one, and up here, looks like another. And these, so this is up 0.4, and this is over 9. So the slope would be m equals rise over run, 0.4 over 9 equals 0.04 continuous. 0.04 continuous. That is that's seconds per centimeter. This is important. So this equals 4.44 seconds squared over meters. Let's just get that into meters right now because we don't want to be dealing with centimeters. We want meters. So that's m. And so we can put that back in here. Extend. So 4.44 equals 4 pi squared over g. So g equals 4 pi squared over 4.44 g. This is g experimental, not real g. Oh, that looks weird. Oh shoot. G experimental equals, that equals about, where'd it go? 8.88. So even though we were on Earth, rewrite that. Even though we were on Earth, it's not 9.8 as we know it to be. So this is in meters per second squared. And so there's an error here obviously, and but this is what we get. And so there's question D. Question D asks, so we've done C. D asks, it wonders if our experimental value for G is within 4% of the real G on Earth, 9.8 meters per second squared. So, so let's see, I'll do a new page. So our G experimental, we got 8.88 meters per second squared. G on Earth, that's Earth. Earth equals 9.8 meters per second squared. And so 9.8 minus 8.88 over 9.8 times 100 equals 9.36% error. So even though we did this, we didn't take their values for their question. We didn't use them. They were there initially. So we did this a different way. We did this on Earth. Question E says that you're in an elevator. We weren't in an elevator. We were in a lab room. And know that the gravity definitely is very close to 9.8. But our error is from various things like it could be from air resistance. It's most likely though from since there's friction in the room. It's not perfect, and so we were assuming no friction, no air resistance, no friction between the rope and the pivot, and so there's it's and also the period we did 10 periods, so that gives it time for it to slow down, and so that's probably the biggest error, the 10 periods and all the friction that slows it down during those 10 periods. So that's why we have this huge error. And so is that D? That's D. And so it's no. It's the answer to D is no, not 4%, 9.36%, which is it's okay, but not great. We could have done better. Yes. So anyway, that is Mech 1, even though we didn't do D, or E, sorry. We didn't do E, which says that you're in an elevator, and these values that they give you are from an elevator. We tried to go in an elevator. It didn't work. Not enough acceleration. So we just did it on Earth, and to see how it went, and this is how it went, and there you go. So thank you. Bye-bye.